Okay, it's time for us to start this morning's session, and it's a big pleasure to introduce Thierry Gallet from Université de Grenoble. He will speak about applications of Arnold's variational principle to the stability of vortices in ideal and viscous flows.
Oh, thank you very much, Elena. Thanks to the organizer for this very beautiful semester and meeting. I mean, it's a very great pleasure to be here in this city with such an impressive history. So as for my talk, I would like to present a method that we are trying to develop with Vladimir Šverak to study the stability of vortex solution in either Euler or Navier-Stokes equation, especially in two space dimension or for axisymmetric flows without swirl, which are the only cases we can treat so far. And the method heavily relies on the geometric ideas that were introduced by Arnold in the 60s to study the stability of stationary flow in ideal fluids. And in particular, we'll make a crucial use of the information given by the second variation of the energy functional at the stationary flow, which is what Arnold told us to do. Okay, so the plan of my talk is roughly as follows. So I will recall some basic fact about Euler equation, but this should be quick here. And I will treat in particular and I will recall what is Arnold's variational principle in this context. And then I will treat in detail the case of radially symmetric vortices, which is the simplest possible case for what I'm going to discuss, but yet is not completely trivial. I'll mention briefly some related global maximization problem. And in the last part, I will give two applications to Navier-Stokes, one to the stability of ozone vortices, which is well known, and another for a new part about viscous vortex filaments. To end the introduction, I should mention that this has nothing to do with turbulence, so I apologize to the organizers, and I apologize to those of you who might have heard part of this talk already on Zoom. Okay, so let's start with the two-dimensional Euler equation. So this should be very quick. So I consider the vorticity equation in two dimensions. U is the velocity field, which is divergence free. Omega is the associated vorticity, and I consider dt omega plus u dot grad is equal to 0. I'm working in the whole plane, but I mean part of what I'm going to say could be also generalized in domains. But for the moment, I will be in the whole plane. And I will make very comfortable assumption. I assume that the vorticity distribution omega is smooth and decays sufficiently rapidly at infinity. For what I'm going to say, this is not the main point, okay? So in particular, I have the stream function defined by this very simple formula. So Laplacian of psi is equal to omega. And when I take the orthogonal of the gradient of the stream function, I get the velocity field. So this is the Biot-Savart law. I know, of course, or we know, of course, that there exists solution in this context, for instance, due to the theorem by Udovich, and that the evolution has many conserved quantities. In particular, I'll use the mass, or I denote by m, the integral of omega, which is a conserved quantity. Okay, so far so good. Now there is another quantity that will play a very important role in my talk, which is the renormalized energy. E is -1/2 integral of psi times omega. Psi is a stream function. So if I plug in the expression of the stream function, I obtain this double integral. Okay. So this quantity is like a little bit like a Coulomb, a repulsive Coulomb energy in two dimensions. If omega was a distribution of mass, this will be just the Coulomb energy in two space dimensions. And this quantity is well defined as soon as omega is a little bit better than integrable. If it's locally a little bit better than integrable and at infinity also a little bit better than integrable, then this integral converges and this is a well-defined quantity. Of course, I make much stronger assumptions, omega smooth and rapidly decreasing, so I have no problem defining this quantity. And also this quantity will be conserved. I mean, we had a very nice talk in the first day by Roman Schvidkoy discussing under which condition the energy is conserved or not. For my solution, of course, it will be conserved. You can make sense of this calculation, and E is a conserved quantity. Finally, if the mass is equal to 0, so if I consider solution with 0 average, then we can integrate by part in here, and you obtain that E coincides with the kinetic energy, 1/2 the L2 norm square of the velocity field. And in that case, it's positive. I mean, this energy has no sign in general, can take both positive or negative values. But this one is positive and is even scale invariant, which was not the case of the generic. Good, so this is very well known. Now let me recall another thing which is well known, which are the orbits. So given one of my vorticity distribution omega bar, I define the orbit of omega bar under measure preserving rearrangements as the set of all omega which are measure preserving rearrangements of omega bar. So for instance, if omega bar takes only positive values, you take all omega which are positive, such as the measure of the super level sets of omega and omega bar coincide for all value of the threshold parameter A. And if omega bar is a sign changing, then you do that for the positive part and for the negative part. Okay, and this defines the measure preserving rearrangement. So the term of orbit comes maybe from this more restrictive definition, which is the orbit of omega bar under the action of the group of measure preserving diffeomorphisms in the plane. If you compose omega to the right by a measure preserving diffeomorphism in R2, then certainly you obtain a measure preserving rearrangement in the sense above, although you may not obtain all the measure preserving rearrangements in that way. So whatever definition you use is not very important for what I'm going to say. But okay, in any case, I call this O of omega bar the orbit under the measure preserving rearrangements. Okay, so the fundamental facts which are well known are that the orbits are invariant under the evolution defined by Euler. If I start from some initial data, the solution cannot visit the whole phase space. It has to stay on the orbit, which is in the best case something like an infinite codimensional submanifold. So there are many, many constraints in Euler evolution, and they are summarized by the fact that these orbits are conserved. And this is because, of course, we have omega is advected by a divergence-free velocity field. Omega at time t is omega at time 0 composed to the right by something like the inverse of the Lagrangian flow map. And this is, of course, a measure preserving rearrangement due to this characterization. Okay, so the orbits are invariant. And then what we call Arnold's variational principle, in the honor of Arnold, is the observation that any stationary solution omega bar is a critical point of the energy functional when restricted to the orbit, assuming everything makes sense, assuming the orbit is smooth so that I can restrict and this is a submanifold or whatever, then it's a critical point. Okay, so this can be proved by a direct calculation, or this can also be deduced for more sophisticated consideration about the Hamiltonian structure of Euler equation. So in short, if you restrict the Euler equation to one of these orbits, formally at least you have a Hamiltonian system, and the Hamiltonian is the energy functional. Therefore, if you have a critical point, a stationary flow should be a critical point of the Hamiltonian, like in any Hamiltonian system. Okay, so this fact was exploited by Arnold to obtain some stability information on the equilibria in the case where this omega bar is not only a critical point, but an extremum, a local maximum or a local minimum. You can obtain information about stability. Okay. Now let's consider how it works in the simplest possible case, where I consider a very simple family of equilibria, which are radially symmetric vortices. So from now on, omega bar of x would be a radially symmetric function with profile omega star. And here is a picture of omega star. It should be smooth, start from some finite value, strictly decreasing, and it should go sufficiently fast to 0 at plus infinity. And these are a schematic picture of the streamlines. Of course, these are concentric circles centered at the origin. So if omega bar is radially symmetric and decreasing in the radial direction, when I compute the stream function, I obtain something which is radially symmetric and, in our case, increasing in the radial direction with my conventions for the stream function. So this is a derivative. This is the formula for the stream function. Okay, now comes an important observation. Since omega bar is radially symmetric and strictly decreasing, and since psi bar is radially symmetric, there must be a functional relation, a global functional relation between both quantities, in the sense that I can write psi bar of x as a function of omega bar of x, and this is globally true for all x in R2. Okay, so I mentioned that because it's well known that if you have a stationary solution to the Euler, the streamlines, which are the level set of the stream function, coincide with the level set of the vorticity, and this is more or less the definition of being a stationary state of 2D Euler. But this doesn't mean that globally you have a functional relation. I mean, locally, near a point which is not a stagnation point, you can write locally such a relation, but there is absolutely no reason why this should hold globally. There are obvious counterexamples. But here, this is true globally because of this hypothesis of monotonicity. Okay, so in this case, I'm in a very favorable situation where I have a global functional relation, and this function small phi, which by definition is a decreasing function in my case, will play an important role in what follows. Okay, now what is this picture with orbits and Arnold variational principle in the case of vortices? Why it's especially simple? I mean, if you have a vortex, one of these radially symmetric vortex, it's non-negative. The orbit consists of all non-negative vorticity distribution for which the radially symmetric non-increasing rearrangement is the vortex. So, I mean, it's just the preimage of the vortex under the map given by the radially symmetric decreasing rearrangement. So the picture is very clear. You have a one-to-one correspondence between the orbits and the vortices, okay? So you can represent each orbit like a big piece of submanifold like this, and you have one point which is a steady state in it, which is the radially symmetric vortex, and then you have a foliation of your phase space by such orbits. So a one-to-one correspondence between orbits and radially symmetric vortices. So it's very clear how it's done. Okay, and now what is Arnold variational principle in that case? Well, it tells you that in fact omega bar is E of omega bar is larger than E of omega for all omega in the orbit of omega bar. So this is the orbit of omega bar. Not only it's a critical point of the energy, but it is the global maximum of the energy in that case. Why is it so? Well, this can be seen from the expression of this renormalized energy here. Omega is non-negative, and of course you see that you have the log function, which can take both positive and negative values. So it's clear from this expression, at least intuitively, that the optimal way of increasing this quantity is you put the mass as close as possible to a given point, like the origin. But within an orbit, the optimal way of concentrating the mass near the origin is the symmetric decreasing rearrangement by definition. So there is something that is called Rees rearrangement inequality, which tells you that E of omega bar is the maximum of E of omega over the orbit. So you have a global version of Arnold's variational principle. Omega bar is the global maximum of the energy. And therefore, we are in the situation where we can use Arnold's ID to deduce information on the stability. Okay, how do we do that in practice? Okay, we'd like to look at the first variation of the energy at omega bar. But this is not so easy because this is a constrained variational problem with infinitely many constraints staying on the orbit. But fortunately, there is a general recipe to transform an unconstrained critical point into a constrained critical point into an unconstrained problem by extending the functional. This is Lagrange approach. So in this case, it's considered, instead of the energy, you consider what I call the free energy, which is this energy, and I add a Casimir term or an entropy term or whatever you want to call it, and I consider this, and I call this a free energy. So the name free energy, I should not insist on that, but in the particular case where phi of omega is omega log of omega, this is like Boltzmann entropy, and this is energy plus entropy, so this looks like a free energy, but it's just a name at this point. Okay, and the function capital phi in principle could be an arbitrary smooth function which vanishes at the origin, but we shall see that we have to choose it as the primitive of this function small phi here. Okay, but for the moment we don't need that. So this term, of course, is constant on the orbit. It takes a constant value of the orbit because if I replace omega by a measure preserving rearrangement, by a change of variable in the integral or by the layer cake representation or whatever you want to use, you see that this doesn't change. So it's constant on the orbits, and therefore it's also invariant under the evolution defined by Euler, because Euler stays on the orbit. So this quantity is again conserved under the evolution defined by Euler. It's a conserved quantity. This is well known. All these Casimir quantities are conserved. So I am adding, so I can consider f instead of e as a function. Now, this term is constant on the orbit, so I mean that Arnold's variational principle is still true for f because I had a function, a constant on the orbit. So it's still true that the free energy has a global maximum at omega bar. So this free energy is exactly as good as the energy as far as the Arnold's principle is concerned. Okay. But now it's easy to compute the first order variation of this energy. You take df of omega bar acting on some vorticity perturbation omega. So you have two terms. So this term, of course, when you differentiate, give this in a straightforward way. And to differentiate the energy, you have to remember that this is a quadratic quantity, and you have to use, for instance, this expression of the energy. And then you discover that the first variation gives my integral of minus psi bar times omega. So this is the total first order variation. And then this quantity is exactly zero if you take capital phi as the primitive of small phi, because then capital phi prime is small phi, and this is zero because of this relation. So then you have, of course, that you have a stationary solution. I mean, omega bar is a critical point of f, not only with respect to perturbation in the tangent space to the orbit, but in all directions, because this is how Lagrange approach works. You extended the functional in such a way that you have a critical point in all directions. And in that case, it's very efficient because computing this expression is extremely easy. It's the easiest way of computing the first order variation of the energy, even when restricted to the tangent space. Okay, the easiest way of doing this calculation is obviously that. Okay, so now we have a good functional f, which has a critical point at omega bar. Let's compute the second variation. The second variation is computed by a similar calculation. So second variation at omega bar acting on, so it's I consider only the quadratic form associated to the second variation. So the energy here, it's easy to differentiate twice because it's a quadratic form. So when you differentiate twice a quadratic form, you obtain twice the quadratic form, right? So it gives you twice omega, and then you have the integral of phi second. But remember, capital phi is a concave function. So phi second is negative. And it's easy to see that phi second evaluated of omega bar of x is minus a of modulus of x, where a is some positive function whose expression is easy to find in terms of the profile. So it's minus, it's the derivative of the string function over the derivative of the vorticity distribution with the correct minus sign to have a positive function. So this is the second variation of the energy. Okay. And well, so far so good. And now we start asking questions. First question, I mean, we started from a construction which tells you that this omega bar is the global maximum of the free energy on the orbit. Okay, so therefore, this second variation should be negative definite, or at least non-positive, when restricted to the tangent space to the orbit. But is it the case? I mean, this is not in the Arnold paper. Arnold treats only examples for which these terms have the same sign. But here is not the case. On the tangent space to the orbit, all the vorticity perturbation has zero mean, so that the energy is positive. And this term is obviously negative. So it's positive minus positive. What is the sign of this quantity? So I know by construction that it should be negative, but can I see it? I mean, I believe in what I can touch, you know. I mean, can I see it? I mean, in which norm is it true? Is it strictly negative? Is it coercive? Can I use it to control the perturbations? So this is an exercise that deserves to be done, and we couldn't find it done in the literature. Okay, so just look at this quadratic form on the tangent space to the orbit. And then we ask a second question, which is even further away from what Arnold could have in mind, is what about the other directions? Suppose that we have done exercise 1. We have checked that this functional f, the second variation, is negative on the tangent space. What about the transverse directions? And here at this point, I'm sure that if Arnold was in the room, he would interrupt me, saying more or less politely that this is a completely stupid question, and I should not ask this question because it's irrelevant to the problem. Why is it so? Because what Arnold has in mind, which is of course very, very clever, is the following one. Suppose that you have a global maximum. On the orbit, it means that the level set are like this. Okay, this is omega bar, and these are the level set of f on the orbit. So if I make a perturbation which stays on the orbit, I can use the energy as a Lyapunov function to prove stability. You are trapped by the level sets of this Lyapunov function. But now, if I make a perturbation which leaves the orbit, then you should go to a nearby orbit and repeat the argument, because at least formally, a full neighborhood of omega bar is foliated by these symplectic leaves, by these orbits. Okay? So in principle, you never have to go out of the orbit. Information on the orbit should be enough to prove stability. And that's true. And that's relatively easy to justify in a finite dimensional situation where you have the implicit theorem, which makes you all this rigorous easily. In the infinite dimensional case, it's a little bit less easy because everything has been formal so far. So this formulation by symplectic leaf, how regular it is near a point. I mean, details have been carried out in a paper by Chauffru and Schwerak a few years ago, and it was not so simple. So it's not so simple to justify this picture, but maybe it's possible. Nevertheless, I insist, I would like to compute the second variation also in the transverse direction. Because suppose that my free energy happens to be a maximum not only with respect to the perturbation in the tangent space, but globally in all directions. And we shall see that this happens, okay? If this is true, I would like to know it, because then if I want to make a proof of Lyapunov stability, I just use F. You took any perturbation, and then you can use it and have the proof like that. I don't need any foliation or whatever. So at least it will be much easier to make a stability proof if I have this stronger property. So this is the reason I would like to investigate that. And the other thing we have in mind is that for the good vortices for which this stronger stability assumption could hold, maybe they enjoy further stability properties. Maybe they are stable not only for the Euler evolution, but maybe also for some perturbation of Euler, dissipative perturbations. And I have in mind, of course, Navier-Stokes equation. When you go to Navier-Stokes equation, you add the viscosity, the whole geometric picture is destroyed instantaneously. The orbits are no longer conserved, the energy is not conserved, but nevertheless, in the application, I will show that if you have this stronger property here, you can save something and obtain some stability result also in the dissipative case. So this is more or less the idea that we want to develop here. Okay, so this was the most important part. Now let's do the exercise concerning the radially symmetric vortices. Okay, so I recall that I'm considering this solution here where omega bar is omega star of modulus of x with some omega star, but here I make precise assumption now on this profile omega star in order to have statements. Okay, so I assume comfortably that omega star is C2, strictly positive at the origin, with vanishing derivative and non-zero curvature, and that omega star is strictly decreasing and it converges to zero at plus infinity. And I assume also that it converges to zero sufficiently rapidly. I mean, this assumption means that omega star is strictly positive and bounded from above by something like 1 over 1 plus r to some power beta. Beta should be larger than 2. Remember that the total mass of omega star should be finite. This is integral of omega star r dr. So, I mean, having such a bound with beta larger than 2 is close to optimal. Unfortunately, omega star should be strictly positive. Okay, this is important, otherwise I'm stuck. So I cannot consider compactly supported vortices. From the point of view of application to Navier-Stokes, this is not a problem because everything will have infinite support. But for Euler, we would like to be able to consider compactly supported vortices. This is very natural, but we cannot. I mean, this is only for vortices with unbounded support. Okay. And then this is the function A. So I recall what the function A here. This is a function which appears in the second variation of the free energy. Okay, this is given by this formula here. So under my assumption, my function A is strictly positive and it grows at infinity, at least like r to the beta with the same exponent beta. Okay, these are my assumptions, which are very general. They can be relaxed in several ways, but I mean, they are already good enough for what I'm going to do. So the second variation of the free energy is supposed to be negative. So I change sign and I consider J as being a quadratic form given by this formula, which I hope to be positive. So I have a local term, which is just weighted L2 norm, integral of omega square with this function A. And then I have minus the kinetic energy. This is a non-local term, and I hope that this is smaller than this one. So it's obvious that the natural function space to study this quadratic form is the function space given by the principal part. Okay, so I define X as the set of all omega in L2 such that this weighted integral converges, and this implies that omega is in L1. So I also assume that my perturbation have zero mass. I make only perturbation which conserve the mass. This is okay. For technical reasons, this is easier. This clarifies the situation. And in the problems I want to consider, this is not a restriction. Okay, so this is my space of perturbation. And then I want to study this quadratic form defined on this function space. Okay, but I still have to explain you what is the difference between the tangent space to the orbit and the transverse directions, because this was all formal. I mean, I never proved that my orbits were smooth submanifolds and I can define the tangent space and so on. So now this is just for as a motivation. Now we have to make the choice, and the choice is made in this case. It's very easy. In my space X, I consider all radially symmetric functions and the orthogonal complement. So it's easy to see that my quadratic form is diagonal according to this direct sum decomposition. So I can compute it on the radially symmetric function and on the complement, and they don't talk to each other. Okay. So I can consider the radially symmetric space and the orthogonal space. And now I claim that the orthogonal space is the tangent space to the orbit, and the radially symmetric perturbation are the transverse directions. So let me make this acceptable. Okay, this is my definition. I can make any definition I want because I will be consistent afterwards, but I suppose that this is the correct definition. I told you that there is a one-to-one correspondence between radially symmetric vortices and orbits. So if I take a radially symmetric vortex and I make a radially symmetric perturbation, I change the profile of my radially symmetric vortex. So I go to a different orbit. So certainly this space is not tangent to the orbit. It should rather be the transverse. And when you stay on the orbit, well, a way of making an infinitesimal perturbation on the orbit, if you take omega bar and compute v dot grad omega bar, where v is smooth and compactly supported and divergence free. This is an infinitesimal motion on the orbit. You can check that this is in orthogonal complement. So this is the decomposition that we should use rigorously. And now the question is clear. I have a quadratic form. I have a function space. I have a decomposition in two different subspaces. I want to know what is the signature of the quadratic form on that space and on the complement. Okay. So first proposition is checking that Arnold was right. So there is no suspense as to what the result will be. Okay. On the tangent space to the orbit, so this space here, the quadratic form J is always non-negative, and it is even strictly positive, coercive, if you restrict yourself to this codimension 2 subspace. What is the meaning of this subspace? Of course, I have translation invariance. If I have a radially symmetric vortex, I can push it in the x1 or in the x2 direction. And of course, this doesn't change the value of the free energy. Okay, so I cannot hope for a strict local maximum because of this translation invariant. But if I freeze translation invariant by going to this subspace, then it's coercive. So we learn that under my assumption, this omega bar is a strict, non-degenerate local maximum of the energy, except for the translations. Okay, so this is not surprising, but this is good to know. Okay. So on the tangent space to the orbit, no problem. We were afraid from by the fact that there are two different signs in this term, but this term is indeed smaller than this one, though it's okay. Now, what about, well, I will not maybe, okay, I will not go to the proof of this. It's summarized in these slides. I mean, this is a general proof which doesn't use any assumption on the vortex because you know, it should be true for any radially symmetric vortex satisfying my assumption. So basically, you go to polar coordinates, you expand in Fourier series, you write in detail the operator, and at the end, you obtain some compact self-adjoint positive preserving operator, which has an eigenvalue 1 with positive eigenfunction, and you obtain, you apply Krein-Rootman to see that this is the spectral, I mean, this is the spectral radius of the operator. It's an argument like that, which gives you. So ultimately, we go down to either Perron-Frobenius or Krein-Rootman or some version of it. It's a general argument which does not exploit the particular form of the vortex. Good. Now, what happens in the transverse direction? In the transverse direction, the answer is Well, it depends on the shape of the vortex. For some vortices, the quadratic form is still positive in the transverse direction. For other vortices, it's not the case. And we are not able to give a simple characterization of those vortices, but we make the following remark that the coercivity in the quadratic form on the radially symmetric subspace, so transverse to the orbit, is equivalent to the validity of this weighted Hardy inequality with a constant, an optimal constant, which is less than 1. So let me explain a little bit like that. I have this function A of R, which is related to the second variation of the energy. I recall that in my case, A of R is strictly positive and it grows at infinity, at least like a polynomial. This implies that you have this Hardy, weighted Hardy inequality. Integral of f squared over r, dr over r, is less than integral of A of r, f prime squared dr over r, for all functions which vanish at the origin at infinity. For some constant ch, this is, I mean, it's known under which assumption of A such kind of weighted Hardy inequality is valid. You only have to open the book by Mazia on Sobolev spaces and you find this criteria, and these are satisfied by my assumptions. So we know that this is true, but what is not clear is what is the value of this optimal constant here. If it's less than 1, then you have coercivity with delta is 1 minus ch. If it's greater than 1, then you have negative directions. Okay? Okay, the proof is just completely written here. It's just a change of variable. You just observe that this is equivalent. So this is not a proof, this is not a statement, it's just a reformulation of the positivity condition. It's related to some weighted Hardy inequality. So let's go to examples. So first family of examples, you have this family of algebraic vortices. Omega star is 1 over 1 plus r squared to the power kappa. Kappa is larger than 1 because I need finite mass. Okay, good. So this is the derivative of the stream function, and this is the explicit expression of my function A in that case. Okay, so for that family, using some inequalities and some analysis of ODEs, it's possible to prove that this optimal constant in the Hardy inequality is less than 1 if and only kappa is greater than 2. Okay, so for kappa between 1 and 2, I have some negative direction in the second variation of my free energy. As soon as kappa is larger than 2, then it's okay for all larger values of kappa. And the boundary case where you have just a neutral direction is what is called the Kaufman-Scully vortex, and we shall hear about this vortex in the talk by Monica later in the day. So this one is very famous. This is one of the important examples in relation with, I don't know, with geometry. And for that vortex, the optimal constant is exactly equal to 1. We know the optimizers and things like that. Second example, the Gaussian vortex, Lamb-Bose vortex, if you want. So Gaussian profile, this is the derivative of stream function, so the velocity field, if you wish. This is the function A. So here you see that A grows at infinity much faster than a polynomial, but this is allowed. In that case, we can also prove rigorously that the optimal constant is less than 1. So we are in the good case, and it can even be computed numerically, but we have an analytic proof that this is true. So conclusion, we didn't clarify completely the situation in this case. For radially symmetric vortices, depending on the vortex profile, you may or may not have the free energy, which is has a global maximum at the vortex. But for many important examples, you are in the situation where the free energy has a non-constrained maximum at the critical point. Okay, good. Now, let me quickly mention something which is probably less relevant to what I'm going to say, but which is the following. Okay, there is another way to look at the problem. We identify some special vortices for which this free energy has a maximum in all directions. But there is a way of producing such kind of example is just by making a global maximization of a given free energy. So let me explain that. So I fix some m positive, which will be the mass of the solution I consider. And I consider ym and the set of all vorticities in L1 such that all non-negative vorticities, such that this integrability conditions are satisfied. And remember, these are enough to give sense to the energy functional. Okay. Now I'm given a function capital phi, not related to any vortex or whatever. I'm giving myself a function capital phi, which would be continuous, vanishing at the origin, and should have some upper bounds. I mean, these upper bounds are difficult to read, but this functional needs not be differentiable to the right at the origin, but should be bounded from above by omega log 1 over omega. So it should not be too bad near the origin. And at infinity, it should go to minus infinity, at least like minus omega log of omega. So I have some assumption on the upper bound of this function. And now consider this free energy. And due to this assumption, I mean, first, due to this condition, the energy part is well defined. And this part, we don't know if it's well defined, but it's not equal to plus infinity. It can be minus infinity because I only have upper bounds on phi, but it cannot be plus infinity. So this free energy is well defined in R union minus infinity, and therefore I can try to maximize it. Okay, and the theorem is that there exists a there exists a maximizer. I can maximize it globally on my set Ym, and there exists a maximizer which can be chosen to be a radially symmetric non-increasing function. Okay, so this produces a whole family for each function phi. It produces a globally maximizing vortex for which my condition of being stable in all directions will automatically be satisfied by construction. Okay, so this is done by direct method in the calculus of variation. I find the proof non-trivial, but probably for experts in such techniques, it's just a routine. But you can, under these assumptions, you can prove that. Okay. Example. So the only example we know is the case where phi of omega is omega log of omega. I mean, up to, don't forget, I mean, don't pay attention to the numerical factor. We can be scaled away. So this is omega log of 1 over omega. This is Boltzmann entropy. In that case, there is a logarithmic Hardy-Littlewood-Sobolev inequality, which tells me that my free energy is bounded from above by m squared over 4 pi. And this is reached if and only if you are a translate of the Kaufmann-Scully vortex. So this Kaufmann-Scully vortex come again. It's the only case in which we know that we have a globally maximizing vortex. Okay, so this is compatible with what we found concerning the detailed analysis in the previous part, but this is an example. Okay, and also I have some cryptic slide about the Legendre transform of the free energy, but maybe I should skip that to have some times to go to the applications. Okay, now let's go to applications to Navier-Stokes equations. So let's first start with the vortices and say, can I use the techniques I have, I mean, the tools I have introduced, like this quadratic form related to the second variation of the free energy, to prove something about the stability of vortices for Navier-Stokes. So if I start with this problem, I have a difficulty at the beginning is that none of this stationary vortex for Euler is a stationary solution for Navier-Stokes because you have diffusion. And of course, you have the spread due to diffusion and you have nothing to counterbalance that. Okay, so there are several ways of avoiding that. And the one that I will choose is the following one. I will concentrate on the Gaussian vortex. So the Gaussian vortex is not stationary, but it's self-similar due to the heat equation. And therefore, if you go to self-similar variables, you have a steady state. Okay, this is not completely honest. I mean, it's a little bit of cheating, but at least in that case, I have a clear-cut formulation of the problem. So I consider the Navier-Stokes vorticity equation, but already in the self-similar variables. So dt omega plus u dot grad omega is equal to L omega. And L is not only the Laplacian, but plus this dilation operator plus 1. And this is the operator that appears yesterday morning in the talk by Maria Colombo, except that she had a 1/2 here because this was for the velocity field, but for the vorticity, this one. Okay, so this is Navier-Stokes in self-similar coordinates, and I consider that. Okay, so now I have a family of equilibria. Omega star is this Ozane vortex, which is normalized to have unit mass. This is the corresponding velocity field. And any multiple of this omega star is a steady state because, of course, the time derivative is 0. The Euler part is 0 because it's a radially symmetric vortex. And in the right-hand side, we have the operator L. And the kernel of L is exactly spanned by the multiple of this Gaussian. This is why we chose this solution here. So any multiple of omega star with some parameter alpha, which is like the circulation Reynolds number, is a steady state, and we like to investigate the stability of the steady states under the evolution defined by this Navier-Stokes equation in cell-similar variables. So how do we do that? Omega, we write alpha omega star plus some perturbation omega tilde, the same for the velocity field, and you obtain the perturbation equation for omega tilde. So dt omega tilde, so you have the nonlinear term, the viscous term, and here you have whatever comes from linearizing the nonlinearity of Euler at the steady state. And these are the additional terms which prevent making a trivial proof just by energy estimate. One term is good, but the other one is more complicated. Okay, good. So I'll consider this perturbation equation in my space X, but I always assume that the mass is 0, and also the first order moments of my perturbation are 0. So this is for to simplify. I mean, this is preserved by the evolution. And by a change of variables, you can always go back to that case. So this doesn't restrict the generality really, but I need that for my approach. Okay, good. So what do I want to do? So I want to construct or to control the size of omega tilde and show that omega tilde goes to 0 exponentially fast as t goes to infinity. Exponentially fast because I am in the self-similar variable. In the original variable, it would be only polynomial decay, of course. Okay, so what do? What should I use? I will use the quadratic form given by the second variation of the energy. This is not the only possibility. I proved stability with Jean Wayne long time ago. We gave a proof of stability of these Ozone vortices using other tools. But here I insist of using this quadratic form. Integral of a omega tilde square. So it's a weighted L2 norm with precisely that weight. And I also have the kinetic energy. And I consider this, and I want to study the time evolution of this functional. So what happens? When I compute the time evolution, I will have viscous terms, nonlinear terms, and terms which come from the linearization at Euler. The terms which come from the linearization at Euler give 0 when acting on the quadratic form J, because the free energy was exactly invariant under the dynamics of Euler equation. Therefore, the quadratic approximation of the free energy, which is the second variation, which is my form J, is exactly invariant under the linearized Euler equation. This is a straightforward calculation. So the advantage of this J is that all this part is immediately cancelled. Okay, you're just left with the diffusion terms and the nonlinear terms. Okay, and in short, so you obtain J dot is minus 2q, where q is the quadratic form which comes from the viscous terms, and n is a trilinear term which comes from the nonlinearity. And in short, this term is good, this term is small. And then you close a differential inequality. So let's look at the quadratic form related to viscous terms. So it's like an H1 version of this one. This is a weighted L2. Here you have weighted L2 of the derivative. And unfortunately, you have a bad term, which a function b, which is a little bit like a. It's given by some explicit expression. So it's not completely clear that this quantity is positive, because it's again something positive minus something positive. But it happens that this quantity is not only positive, but it controls J. So here it's a point where I feel a little bit uncomfortable, because I do not know if this is an accident or a general fact. It's not obvious at all. You have to work a little bit to prove these results. This is related to locating the spectrum of some self-adjoint operators involving these vortices in the coefficients. So we can prove that. But since I do that only for one vortex, I cannot tell you if it is a general fact. If I could do that for a family of vortices, maybe we can start discussing like in the previous case. But I don't know how to formulate this for more general vortices. We are thinking about it, but for the moment, I do only that case. Okay, so let's take this for granted. This is a miracle. This Q controls J. And the nonlinear terms N is bounded by J times Q1/2, so it can be absorbed. So you go back here, and you obtain a differential inequality, like J dot is minus a constant times J, so you have exponential decay. The proof is completely trivial, and this is why we do it like this. This choice makes all the dangerous terms disappear, and you are left with something which is basically trivial. Okay, so this is why I think this is interesting. And you see that we have used in that case that my vortex was globally maximizing, because I need that to be coercive. It has negative direction. I do not control the perturbation. So here I use the fact that my free energy was coercive in all directions in order to have this quantity. And this is good for Navier-Stokes. So the final statement, this one, uniform stability of ozone vortices, there exists positive constant C epsilon nu, such that for all alpha, for all initial perturbations which are sufficiently small in my space, then the solution decays exponentially with this very simple estimate. So this proves a uniform stability. This is uniform in the parameter alpha. So of course, first, this is exactly the analog of my result with Jean Wayne. We use different function space and the proof was simpler, but the proof was using in a fundamental way the invariance and the rotations, because I use some other conserved quantities related to the second moment, the moment, second order moment, which disappear immediately if you don't have radial symmetry. Whereas here, in principle, I could do that for a much larger class. I mean, the second variation of the energy could be good also for less explicit and less symmetric equilibria, provided you can prove the information on it. But this is conceivably possible. Whereas the trick that we use with Jean Wayne, and is also used in the Marchioro and Pulvirenti and so on, this is requires radial symmetry fundamentally. If you don't have that, you cannot start. Okay. And also, I should mention that this is the result is completely obsolete by now, because for large value of alpha, you could use, of course, the part that was neglected, this part here, to obtain better result using inviscid damping and enhanced dissipation and all that. So there are results that use that, but here it's a result that is uniform in alpha, but we do not exploit the good effect of alpha when alpha is large. So this is not the best result so far, but it's the basic result obtained in a very cheap way, assuming that you have all this information about this quadratic form and so on. First application, but the real application we had in mind, the reason we developed all that is not to do a new proof of something which is known, but something we couldn't do, and this is related to viscous vortex rings. So Monica will speak in detail about vortex rings, so please be patient. But a vortex ring is a solution of 3D Navier-Stokes or Euler, where the vorticity is concentrated in a solid torus. So this is a picture. The black arrows represent the velocity field, and the vorticity should be in azimuthal direction inside the torus. It's like a loop of current in magnetostatics, okay? And this is not a steady solution. It moves with some speed, and the speed is related to the three important physical parameters of the vortex ring. Since this is a torus, there is a large radius capital R and a small radius small r, and gamma is the circulation, which is the flux of the vorticity vector through any cross-section of the vortex. And the asymptotic formula for the speed is gamma over 4 pi r. This is the velocity times the logarithm of the aspect ratio of the torus. And this is a simple example of the binormal flow formula. Okay, so this is what has to be justified. So there are many approaches to that, constructing exact solution in moving frames. But here we would like to justify it within the Navier-Stokes equation. So what we want to do is the following. We consider axisymmetric flows without swirls. So we'll speak about axisymmetric solutions in the next talk. Okay, so just very briefly, you introduce cylindrical coordinates in R3. You consider velocity field, which depends only on the radius and on the vertical coordinate, and which are also have no swirls. So it's also in the radial direction or the vertical direction, but not in the swirl direction. Okay, so the vorticity has only one non-zero component in the swirl direction. You have incompressibility condition, you have some boundary conditions, and you have the evolution equation for the axisymmetric vorticity. So now you have in a half plane, okay, which is r, the radius, and z, the vertical coordinate, like that. And you have this solution, this equation, which looks very much like the 2D vorticity equation, dt omega plus u dot grad omega. Here you have a vortex stretching term, a very gentle one, but still a little vortex stretching effect. And here you have a Laplacian with an additional term which takes into account the fact that omega is not a scalar, but it's the only non-zero component of a vector field. And this gives you some geometric term here. Okay, but this is a perturbation of the 2D equation. Okay, and what we want to do is to solve this equation with a Dirac mass as initial data. Gamma times the Dirac mass at R is equal to R bar, Z is equal to 0, for instance. Okay, so a Dirac mass corresponds to a vortex filaments, a vortex ring with 0 aspect ratio. So this one, of course, for Euler, you cannot consider because it will travel with infinite speed. But for Navier-Stokes, due to diffusion, the speed will be finite for all positive times. The displacement will be finite. So in principle, you can study that solution. So we had a previous work with Schwerak showing that, in fact, the Cauchy problem for with such kind of initial data is globally well posed for the axisymmetric Navier-Stokes equation. Given gamma and the initial position of the vortex, which is my dot here in my plane, I have a unique global solution of the axisymmetric vorticity equation, which is uniformly bounded and which converge weakly to the Dirac mass as t goes to 0. So this is proved, this is published in 2019, okay? And what we would like to do is to describe how this solution behaves on a short time in the vanishing viscosity limit. And this is more difficult. And this is the tentative result. I mean, this is still in preparation. Otherwise, I would have presented this in detail. I think that if I take a small time t, and I consider uniformly in time over 0 and capital T, the difference between the solution and this approximation goes to 0 in the vanishing viscosity limit. And this approximation is a viscous vortex ring with Gaussian cross-section, which is exactly what you'll obtain by solving with this Dirac mass, not the axisymmetric vorticity equation, but just the heat equation or whatever. This would give to leading order this. So omega minus this approximation, this goes to 0. And now this vortex ring is located not at the initial position, but at something which depends on time. So the radius changed a little bit, but in the vanishing viscosity limit, you can consider it to be constant. But the vertical coordinate, of course, moves quite a lot. I mean, the derivative, the vertical speed is this fixed speed, which is related to the circulation and the radius. And then you have log of the aspect ratio plus a constant plus higher order terms. The constant is explicitly known. It depends on the speed. I mean, it's due to the fact that you have a Gaussian vortex. And this is, okay, this diverges as t goes to 0 and also as nu goes to 0. So the speed is very, I mean, you have infinite speed at initial time, but the displacement is finite. The displacement goes to infinity when u goes to 0, of course, because the speed, I mean, this effect is stronger and stronger, but still we claim that we can prove that result. What is the connection of this result as with what I said so far? Let me finish with that. Just waving hands. What do we have to do to prove that? Well, we have to construct a solution of this, okay? So we first construct an approximate solution, and the leading order of this approximation is this viscous vortex ring. But this is not necessary, this is not sufficient. We construct an expansion in two small parameters. One parameter, epsilon, is square root of nu t divided by R0. This is the aspect ratio of my vortex ring. This is the cross-section, and this is the radius. And the other small parameter, delta, is nu over gamma, which is like the inverse of the Reynolds number. These are dimensionless parameter, and we make an expansion of the solution. The leading order is that, but we make an expansion to order 3 in delta and epsilon. Okay? And once we have this very accurate approximate solution, this is cumbersome but easy. Okay, you just straightforward but cumbersome calculation. So once you have this approximate solution, we consider the true solution as the approximate solution plus a correction. And we write the equation for the correction. And the structure of the equation for the correction is exactly the same as for the perturbation of the vortex previously. dt of the correction plus terms which come from the linearization of Euler, plus nonlinear term, plus diffusion terms, plus a remainder term, a source term, which takes into account the fact that my approximation was not an exact solution of the problem. And I just want to show that this correction remains small. And for that, I have to controlling in a norm which is independent of the bad term due to Euler, because the bad term due to Euler will have a 1 over epsilon square in front. They are the solution we construct are extremely singular. St goes to 0 or nu goes to 0, so have very, very fast velocity fields. So you have this advection term are very large, but they just average the solution. Okay, so we need a norm which disregards that, and we were unable to guess just weighted L2 norms of omega that would do the job. But if we take the free energy associated to a stationary solution of Euler, a vortex ring in that case, and we take the second variation, then the quadratic form we obtain does the job in this problem exactly as it did the job for the Haussane vortices. So in that case, we were not able to guess, maybe it's not the only way of solving the problem, but that is in our approach, we are not able to guess in which function space we can control this difference. But using Arnold and these geometric ideas, we have a guideline, we know a recipe for producing a quadratic form which is coercive and which disregards the bad term, the worst term in the equation. And therefore, we can close this proof. And I suppose I can also stop my talk now because to leave time for discussion.
Questions?
Okay, thanks for the wonderful talk. I think I'll have infinitely many questions, but I just ask one. So you showed us that for your vortex, you do have a weighted Hardy inequality. And I kind of have the feeling that if you have that, when you go to the Navier-Stokes, you actually have a spectral gap thanks to this Hardy inequality. Do you believe that is it possible to quantify that spectral gap in terms of the Hardy inequality? And if you have a quantification in terms of parameters, probably you would also see the enhanced dissipation rate in your convergence result.
I thought about that, but maybe it's just stupidity. I was unable to really formulate the problem for the Navier-Stokes for a vortex which was not the Gaussian one, because this is because of this story of going to self-similar variables. If you don't go to self-similar variables, you never have a spectral gap because this is created by this mechanism. But this mechanism is related to Gaussian because in this operator, the kernel is precisely the Gaussian. So I'm just missing a connection here. How to formulate the Navier-Stokes problem? I think there is a question which maybe is feasible but has not been investigated. Suppose that for Navier-Stokes, you start with some radially symmetric profile. Okay, so then you know that it evolves according to the heat equation and will become eventually Gaussian or whatever, but it evolves according to the heat equation. And now you take a very small perturbation, and can you prove in the vanishing viscosity limit that this perturbation remains small and that the vortex still evolves according to nearly the heat equation? I don't know how to do that, but I suspect that this kind of tool could be able to do that. In that case, this is what we are doing, except that due to this trick of going to self-similar variable, we can freeze the vortex and considering, but this is exactly, if you go back to the original variables, I start with a Gaussian vortex plus a small perturbation, and I follow I control this perturbation all the way to infinity in time, but during that time, the vortex will spread out and things like that. Okay, we have a way of translating this into a fixed point problem for Navier-Stokes due to the self-similar variable, and I don't know how to reformulate the same problem for a general. But I would like to investigate the relation between, okay, having this spectral gap and whatever the effect of the viscosity will be. But for the moment, I don't know how to formulate this cleanly. Maybe we can discuss that. For the moment, it's just an example.
Okay, thank you.
So you saw this kind of a critical vortex, this Kaufman skull vortex, Scully vortex, and this was not a global maximizer if you consider the constraint problem, basically with the Lagrange multiplier, if I'm correct, because the
it's a global maximizer.
It's a global
It's a global maximizer, but it's the case where if I take the second variation of the free energy, I have a zero eigenvalue. So it's not strict. I mean, it's here. Let me show you here exactly. So this constant is less than 1 if and only if, but it crosses 1 exactly at k is equal to 2. So you have an extra, not only you have the translation invariance, but you have an extra direction which is related to scaling invariance, because this is linked to conformal geometry. But this doesn't prevent it to be a global maximizer.
Of course.
No, it's a global. It's the only case where we know for sure that it's a global maximizer, because we have this beautiful logarithmic HLS inequality.
Yes, yes. And so what is then the relationship? So when you took this other additional function with the Boltzmann, like with the entropy functional,
yes,
the fact that it maximizes this function, what is the relationship with Euler?
Well, okay, good. You are asking about why did I mention that? I mean, is okay. With this procedure, I obtained some omega star, some radially symmetric vortex. Okay, I didn't say that it has a smooth, strictly decreasing profile. Okay, but formally, this is a radially symmetric solution to Euler, for which, by construction, the free energy is globally maximizing. So at least in particular, it has a second variation, which is negative in all directions, because this was constructed like that. So the question is what we can reach with this construction. So it's just to say that we know only explicitly one maximizing vortex, which is Kaufman-Scully, but in fact, there are unboundedly many, because I can construct them by this. There are technical issues with this construction, which I didn't want to mention. In particular, for all radially symmetric vortex, the function capital phi that we obtain is concave. But here we didn't assume that phi is a concave function. If it's not a concave function, what happens to the maximizer and things like that? So we have some preliminary information about that. But it's just to say there are many of these vortices which are globally maximizing, because I can produce them. I suppose that if phi is a smooth concave function, this is also smooth. And then I produce smooth vortices which are globally maximizing. There are many. I don't do anything with them then, but just there are many. We are not discussing an exceptional set.
We have a couple of questions online.
And also questions at the back of the room. It was.
Can unmute yourself and ask the question. Anne-Laure, perhaps you can unmute yourself and ask the question.
Yeah, sure. Hello, and thank you very much today for the beautiful talk. I have a question on the very last theorem that you presented, the one which is still in preparation. So I'm not sure I understand everything correctly, so tell me if I'm wrong. But so here you construct one solution that has the behavior that you mentioned on this slide. And I was wondering whether you had some kind of, I don't know, maybe stability or something, or you expect, for instance, that any global solution having the behavior I and too high behaves like this.
I mean, there is a unique solution. I just solved the Cauchy problem with a Dirac mass as initial data. So you have absolutely no choice. And as for stability, I mean, the method we use to prove this asymptotic result use information about stability. So I also know that this is sort of stable. I mean, in the spirit of some papers by Jacob and collaborators, we could also add probably some smooth part and have some stability result here. I just take one Dirac mass as initial condition here. Okay.
Okay. So, for instance, if your initial data is close to a Dirac mass in some sense, like some Wasserstein distance, or I don't know, then you expect your solution to be globally close to the vortex string you're constructing, right?
Or at least for some time, and you have to be very careful in which sense you say that you are close initially. Okay, so there are some for the much more difficult problem of the vortex filament in 3D. There is a paper by Jacob Bedrosian and Pierre Germain and I don't know the first name, Harop Griffiths. And they consider also more general initial data, Dirac mass plus some smooth part or some part. And in that case, it's in 3D case, so it's even much more general, but they clarify in which sense you can hope stability for a stability result in that. So here I just take for simplicity the unique problem. You know, I didn't mention, but if I start with one Dirac mass in the 2D case, I get the Ozane vortex as a trivial self-similar solution. So I'm just trying to reproduce what is Ozane vortex in the axisymmetric case. So this is just constructing a particular solution.
Okay.
But it should be stable and yeah.
Okay, thank you.
Thank you.
Okay, I think there are 2 more questions online. So the first one is from Maria Colombo. Maria, do you want to mute yourself perhaps and ask the question directly?
Yes, thanks. So I wanted to ask 2 things. First, can you consider, can you use your variational method somehow to prove instability of vortices?
I mean, there are instability results in Arnold's work. They under some conditions, and here we focus really on stability. I mean, that's true, but in some, it's not because that. I mean, it's not easy because it's not because what you consider could be a Lyapunov function is not coercive that you have necessarily instability. Okay, but there are results in Arnold relating to instability, but we didn't try to implement that. I mean, I suppose you have in mind that if omega star is not a radially symmetric profile, but it has a bump or something like that, one could prove instability like what you used in what Wyshik used to produce an example. But we have nothing new to add to this.
Okay. And the other question is, can you consider stationary solutions with the right-hand side? For instance, for Navier-Stokes in the last part, I don't know.
Well, it probably depends when you put in the right-hand side, but no, for the moment, it was really Navier-Stokes. I suppose that some kind of sufficiently irrelevant forcing could be included, but I'm not sure. Then, okay, everything is in the detail of, for the moment, it's just Navier-Stokes evolution.
Thanks.
Okay, there's one final question. Robert Kerr, do you want to ask your question?
Okay, so right now I'm in Kenilworth on the other side of England, but I'll be in Cambridge this evening, hopefully towards the end of the banquet. My question isn't really a question, it's a point of something I've been working on and done in the past. I do very few 2D calculations. Almost everything I do with vortices is in 3D. And what I discovered about 10 years ago is that there's an inherent problem with perturbed Gaussian vortices in 3D, where they are unbalanced in a sense that comes from compressible Navier-Stokes and also atmospheric dynamics. And the nature of the imbalance is that the perturbation creates a ghost vortex around the main vortex. And this does horrible things to the vortex dynamics. I'm not quite certain myself. I have a special example of this from 10 years ago where I sort of introduced the idea, but it was in a conference proceedings. And I'm currently working on doing this more explicitly. And what I'm hoping is that once I'm in Cambridge over the next 2.5 days, that I can have discussions with you and anyone else doing things like colliding vortex rings, the Tim Nichols experiment that used to exist on the other side of Cambridge, and get some ideas on what is going on when I observe these effects. So it's a comment for us to discuss later. That's what I wanted to say.
With pleasure. Yeah.
Okay.
Thanks.
Okay, I think if there are more questions, we should leave them to the tea because we have a group picture now. So let's thank Thierry for a beautiful talk first. And Anna, do you want to say something?
I would just say stay in the